Now that we know how to do a one-way ANOVA, we're going to add to our skills by doing what's called a blocked ANOVA, or a randomized block ANOVA. In this case, we're going to consider our factor and any differences that might exist between the levels of the factor that are specific to individual differences. Those individual differences are going to come from our research design. In fact, this design that we're going to be using is a lot like a repeated measures ANOVA design, and I'm going to compare and contrast so you can see the similarities and differences between them. So here's our setup. Juan is interested in the best time to plant Arabica beans. Thinking that he should control the variability between the beans, he plants 6 in late spring, 6 more in the summer, and again in the early fall. All of the Arabica beans are selected from the same 6 high-yield plants and would be considered twins, or similar enough that we'll group them together. So with that setup, we're going to use a very specific test. We're going to choose the appropriate test, and it's called a randomized block ANOVA. Think about what we are controlling as a constant versus where variability would lie in this model. So the first thing you might notice is that the soils all look the same. That's because location is a constant. We're growing them all in the same place, but we're growing them at different times. The times will be late spring, summer, and early fall. Therefore, the differences that we're interested in, our treatment effect, will be due to time of planting. Now, the way that we're going to do this is we'll get high-yield plants, we'll get beans from those 6 different plants, and we're going to keep them separated from one another. So from the first plant, plant number 1, we'll have 3 beans, and we're going to plant those in our first block. For each block, we'll have a bean from plant 1 in that first, second, and third block, and the same is going to be true for all of the other plants. For plant 2, 3, 4, 5, 6, 1 bean from each of those plants is in each of the blocks. And that's what makes these blocks homogeneous. We have the same characteristics in each block. So there shouldn't be any difference. They're all twins, right? Each of those 3 beans, 1, 2, and 3, are pulled from the same plant. Except it's a little bit like, I don't know, maybe you and your siblings. You're probably a lot more alike than you are different, but there's still going to be some differences. So we're going to assume that there is some differences even among these twins, beans from the same plant, they're planted those 3 times, and that is the variability that we're going to want to control for. We're going to extract that variability from our model, leaving us with just a clean measure of effect size. Our research design, we have 2 or more groups. In this case, the factor is season, and the 3 levels of that independent variable are the 3 seasons that we've already discussed. Our dependent variable is going to stay the yield, which can be measured as a mean. But the thing that we're adding now is the blocks. This additional measure of variability that we're going to control for, remember, analysis of variance. Blocks, homogeneous groups, they're all the same kind. The control for variability in the dependent variable, the amount of yield, and that variability is not of interest. We're not interested in the differences between the twins. We're interested in the overall effect of when is the best time to plant our beans in the season. And I've said that this model is really very similar to repeated measures. In fact, Sophie's fun fact, did you know that a blocked ANOVA and a repeated measures ANOVA are really the same test? It's only a difference in how we interpret them. We set them up slightly differently. So remember, in this case, I have 3 beans drawn from plant A. I'm treating them as twins, or maybe triplets if you want to be more specific. There's going to be some random variability between them. But I have 6 plants from which I have chosen beans. So here's a simplified version of how those blocks would look. All of the beans that I've chosen from plant number 1, so I'll call that A1, in each of my blocks, I'm going to plant an A1. And in each block, I'm going to plant from the second plant A2, 3, 4, 5, and 6. blocks. I have a total of 6 beans drawn from the 6 plants. Each block is going to have 1 bean from those 6 plants. They're planted at different times. A repeated measures ANOVA is a slightly different research design, and what repeated measures does is it controls for individual differences by using the same people over and over again. I can't do that with my coffee beans because you can't plant the same bean twice. So I've got to use an analog for that. That's where the twins part comes in. What I could then do is take the same people and measure them at 3 different time periods. I measure one group at time 1, which I might call a baseline. This is the start before we do anything else. And then I measure that same group again at time 2. That's my 1-month follow-up. This is after the training has occurred. So I should see a difference, an improvement because of the training. But does that training last beyond just the time that we're in the classroom? I'm going to test that same group again at time 3, a 1-month follow-up, to see whether those differences endured or did they slide back toward where they were in the beginning. Individual differences are being controlled for by using the same individuals across all 3 conditions. So if you think about the block design, that's not the same people, that's similar people, or twins, versus this design for the repeated measures where I literally have the same people in each of the conditions. Here's what our data look like. Let's talk about the sources of variance. Where's all this variability coming from? Our main treatment effect is coming from what time of the season we plant, late spring, summer, early fall. And we will see the results of that in the means for each column. There's our 11.5, 10, and 9. That is the effect for the season. What we're going to control for is the variability due to the blocks. In other words, the plants from which we have drawn these beans, they all grow a little bit differently. And that variability we're going to see in the means across these rows. These are the block means. So any variability that's coming from these block means, that is going to be measured and then subtracted from our total variability to give us only the measure of the treatment effect. So now we know what test we're going to use. Let's establish the null and the alternative hypothesis. In this case, we're going to assume that the growing seasons give us the same type of yield. It doesn't matter when you plant the beans, you'll get the same yield at any time of season. Or all of these seasons have the same mean. Hence, h sub 0 colon mu1 equals mu2 equals mu3. Our alternative hypothesis would therefore be h sub 1 colon mu1 does not equal mu2, does not equal mu3. And what we are saying is that there will be differences in there somewhere. One of these growing seasons is going to be better than one of the others. We don't know which one, we're not establishing a direction, but we're wanting to test. Is there a difference in yield based upon the growing season? For step 3, we'll select the criterion for statistical significance. And as we usually do, we're going to keep our alpha level set at 0.05. Remember that our f-test, because it uses squared values, can't have any negative numbers. The lowest value we could get is a 0. Therefore, there are only positive values. The f-test is just naturally a one-tailed test. The f-test is also an omnibus test. We're not determining, if this group is better than that group. We're just simply asking whether differences exist. So it doesn't make sense to talk about one-tailed, two-tailed tests. It's naturally a one-tailed test, and we're getting a result that is telling us whether there are differences in our model. To find out where those differences lie, we would need to do a post hoc test. The degrees of freedom now become a little more complex because we have one additional source of variability. We're going to need to account for the blocks. The degrees of freedom for the blocks is going to be b minus 1. So remember, there were 6 plants that we chose, each one giving us a bean that was planted in each of our blocks. Therefore, 6 minus 1 gives us 5 degrees of freedom for the blocks. For the treatment, there are 3 planting seasons. K equals 3. The degrees of freedom for the treatment, or planting season, is 2. The degrees of freedom for the error is 10 degrees of freedom error. And our degrees of freedom total, as it always is, n minus 1. There's a total of 18 beans being planted, giving us an n minus 1 of 17 as our degrees of freedom total. We can calculate a critical value using our spreadsheet. We can go to the critical value effect size tab and enter the degrees of freedom between and within. Now remember, we're controlling for blocks, so we're only going to focus on the actual treatment effect. Therefore, we're going to enter 2 for our degrees of freedom between and 10 for our degrees of freedom within, or our degrees of freedom error. And we're keeping our alpha level at 0.05, although that can be changed to 0.1 or 0.01. With 2 and 10 degrees of freedom, the critical value is 4.103, and this is specific to the treatment effect. That's the one that we really want to know about. And with that, we are ready to calculate the test statistic. So for this, let's go back to our Excel spreadsheet. We're going to be using that same analysis tool pack that we did previously, and we're going to be calculating the findings for our randomized block ANOVA. So let's start by going to the Data tab in the ribbon. Click on Data Analysis. For the data analysis, we're going to use ANOVA 2-factor without replication. Now click OK, and let's tell Excel where the data are. As we've done before, we want the header and the raw data only. For the output range, select C3 through F9. And then click Labels so that Excel knows we have headers across the top of our columns. We'll leave our alpha level set at 0.05, although that can be changed if we would choose to do so. Click on the Output Range Radio button, and then we're going to put our output in cell C14. When you've done that, click OK. Excel will cuss at you saying there's already stuff in C14. Yes, yes, we know. Just dismiss that error, and let's take a look at our findings. We were interested in what growing season is best. Planting at what time gives us the highest yield. And what we see is that the highest yield is in late spring. We got an average of 11.5. Okay, that's pretty good. That means we should always plant in the late spring. Well, before we conclude that, let's determine whether there was a statistically significant difference in the outcome. In other words, it was a little higher in spring, but is that truly different, or is that just a result of randomness and error? Now we're going to take a look at our ANOVA summary table. The first thing that we're going to see is the p-value for the rows. That's our blocks. Here the p-value is 0.07, which is not less than 0.05. What we have is a non-significant difference for blocks. So to interpret that, we're saying that there really is no difference between the twins. That when you pull the berries, the beans from any of these plants, they're all growing pretty much the same. Any differences that we're finding are fundamentally due to the time or the season in which they were planted. However, we're still going to report the findings for a time of season, having already removed any variability that can be explained by the blocks. This is giving us a better measure of the effect. The treatment effect, our p-value is 0.0044. Yeah, that's a statistically significant finding. We see that our f-value of 9.3 exceeds 4.1, statistically significant effect for season. So therefore, we're going to reject the null hypothesis that says there's no difference and conclude that there is a difference, a statistically significant difference, that these 3 populations are not the same. That in fact, planting at different times of the year does have an effect on the outcome of yield. To do a Fisher's post hoc for this example, I've set the alpha level at 0.05. Given the settings for our test, the Fisher post hoc t-value is a 2.228. Our difference of 1.5 exceeds 1.2, it is significant. Our difference of 2.5 exceeds 1.2, it is significant. But summer versus early fall, that difference is only a difference of 1. It is non-significant. What we have are some seasons where we have better growth. Of course, now we need an effect size. So for that, let's go to the effect size tab on our Excel spreadsheet. And you'll scroll down until you find blocked ANOVA. This is where the information is going to get pasted. The information that we need, however, is on the blocked tab in the ANOVA summary table. Grab everything from the sum of squares for rows, that 13.83, all the way down to that empty box for the F critical total. Select copy, and then jump back to the critical value effect size tab and paste where you see sum of squares rows. Now, once that information is pasted in, the partial eta squared and the partial omega squared will come to life, and we can see what those effect sizes are. Now remember, we're not interested in effect sizes for blocks, only for the treatment effect. We're going to ignore the effect sizes for blocks and focus only on the effect sizes for the row that says columns, which is the treatment effect. Remember that our eta squared is the measure of effect size for our sample. Omega squared is the effect size for the population. That's the one that I would prefer to report. So I'm going to report an effect size of 0.49. That means there is a statistically significant difference, which we determined from our F table, and it's a large difference. We can determine that from our effect size. We did our post hoc test to find out where those differences actually lie, and so now we can interpret the results and write up the findings. Let's review what we learned from our F test. We established a critical value of 4.10 with 2 and 10 degrees of freedom, and yet our test statistic was 9.8. That exceeds 4.1. Their test statistic is over the fence. It is significant. We're using an alpha level of 0.05. Our probability value is 0.04. That is way smaller than 0.05. P less than 0.05 tells us the same thing as our findings for the critical value. There is a statistically significant difference. We reject the null hypothesis that says there's no difference. We accept the alternative that there is a difference. And then we did our post hoc in order to find out exactly which groups differed, or in our example, which of those seasons was different from which other seasons. We can write this up in APA style. Here's what our ANOVA summary table would look like. I'm going to change the title for the source to be blocks and treatment. We'll leave error as its own terminology. And if you want to see the full APA write-up, that will be in your course notes. You can see exactly how I walked through testing assumptions and designing this research and how I would write that up in APA style. And that, my friends, is how you do a randomized block ANOVA. So what we're going to do next is a type of ANOVA where we have not one but 2 independent variables. This model is going to allow us to test the main effect of one independent variable, the main effect of a second independent variable, and more importantly, a potential interaction that may exist between those 2 independent variables. And that is what we're going to do next.